Here are solutions to homework set number 14 for ECE 111, Introduction to ECE. This homework set looks at using Matlab to solve problems that you'll run into when you take signals and systems and designing filters. Now, a filter is any circuit whose gain changes with the frequency, which pretty much means any circuit with inductors, capacitors. You've got analysis and design with filters. With analysis, you know what the input is, find the output. With design, it's you know what the filter's gain versus frequency should look like. Come up with a filter. Start out with analysis. If I have a transfer function relating x and y, this represents a differential equation. And where that comes from is we assume everything is in the form of e to the st. So what happens when I differentiate, I get s e to the st. So differentiation multiplying by s are the same thing. S is an operator, meaning derivative. So if I have this transfer function relating x and y, that really means the following differential equation. Cross multiply, multiply out the polynomial, and then you have s means derivative, so that's the third derivative of y, second derivative, first derivative, just y. First derivative of x and x. So this differential equation corresponds to that transfer function. And anything that satisfies that differential equation will behave the same. It could be a circuit, could be a mass spring system, what have you. In electrical computer engineering, this will typically be a circuit. So this would be a circuit with, say, 3 capacitors in it, third order differential equation. Part B is analysis. Suppose the input is a constant. Find y. Now when you take calculus, I'll solve this differential equation with that forcing function. That's the hard way to do it. There's a shortcut. You'll get to this when you take circuits 2 and signals and systems. Here's the transfer function. That's the gain. So oftentimes this is written as g of s. It's the gain between x and y. And it's a function of frequency, function of s. At DC, s equals 0. Again, everything is e to the st. So if I have a constant, 4 times 1, s equals 0. So e to the 0 is just 1. DC s equals 0. This is the gain everywhere. All I care about is what's the gain at 1 times the input. The input in this case is 4. That represents the constant of 4. And what I get in Matlab is evaluate at s equals 0 times x, I get 106. So if the input's a constant of 4, the output should be 106. Now I can check that in CircuitLab. This is kind of a neat feature in CircuitLab. It just came out recently. If I build a system, let's bring this down. I can build a system, oops, come back. Scrolling down, here is the transfer function block. This is kind of a new feature. Drag it over, double click on it. I can input the transfer function. So this is kind of the way you'd write it. It's 100, s plus 4, s plus 1, s plus 3, s plus 5. If the input is a constant, which I can do with a constant, this guy, or I can treat this as, well, let's do it that way. Let's pull this down. Make that a constant of amplitude 4. Should I do that right? So the input is 4. Find the output. So now I can go under simulate, do a DC simulation, expression. Here's x and y. Solve. Output is 106. Same thing that I calculated. Could also do that in time domain. This is kind of boring, but go to time domain, let's run it for 10 seconds. Run it. There's the input, there's the output, that's DC. Again, constants. I could do the time domain, but it's kind of boring. Where it really shows up is the sine wave, part C. So if my input is a sine wave, find the output. In this case, in phasor form, x is 0 minus j5. The real part is cosine. There is no cosine. The complex part is minus sine. So 5 sine is 0 minus J5. This guy right here is the frequency. The frequency is 6 radians per second, so S equals J6. This is the gain everywhere. All I care about is what's the gain at 6 radians per second times the input at 6 radians per second. Analyzing, or in Matlab, here's S, here's X, here's Y, that's Y. In rectangular form, the real part's cosine minus J is sine. Or in polar form, the magnitude is the amplitude, the angle is the phase in radians. I could check that in Circuit Lab. Going over to Circuit Lab. Let's get rid of this. I've replaced my sine wave. Again, the input is 6 radians per second. I need to convert that to hertz. So 2 pi times frequency is radians per second, or 6 divided by 2 pi. That's your frequency in hertz. Amplitude is 5. If I simulate, here I've got to go under time domain. Let's run it for 10 cycles, 10 milliseconds, 1,000 times smaller. Run it. Here's what I get. So there's the transient. I want to get to steady state. Here's the output. The output is 11.13 volts. What I calculated is 11.31 volts. Basically the same thing. So if I have a known input, like 4 is sine of 5t, I can analyze a filter pretty easily. You just plug in S equals j omega, convert x to phasor form, you get y. A second way to do analysis is graphical. If I don't know what the x is, but I know its range, like x is something between 0 and 30 radians per second, I can plot the gain versus frequency. To do that, I'll let frequency go between 0 and 30 radians per second, as is j omega. The gain is pretty much the way you write it. 100 s plus 4 over s plus 1, s plus 3, s plus 5. Note that I need to use this dot notation. That tells Matlab this is a 3000 by 1 array. Don't treat that like a matrix. Treat that as 3000 separate numbers. Analyze g of s at each frequency separately. When I'm done, I get a complex number, plot the magnitude versus frequency, and here's what I get. So at DC, s equals 0, there's the gain. At 6 radians per second, here's the gain. And if I pick another frequency, like let's do 3 hertz, that's about 18 radians per second, gain ought to be really small. So let's go over to Circuit Lab. If the input was 3 hertz, and then run it. Now let's go simulate. Let's do it for 2 seconds, 2 milliseconds, 1,000 times smaller. Oops, 2 seconds. And I'm still in the transient. Let's try that again. I need to let it go long enough to get out of the transient. Okay, 10 seconds. Here's your steady state response. Zoom in on it. You see the output. Input was 5, output is 1.38. That's what's showing up over here. The gain is dropping down. So that's kind of graphical way of describing how the filter behaves. Let's try that for another filter. If here's a filter with complex numbers, again, Matlab doesn't really care. Here's frequency goes 0 to 30 radians per second, S is j omega, here's the gain, pretty much the way you write it. Plot frequency versus magnitude, and I get this graph. So what that tells me is when the input is small, the gain is about 0.3, goes up to 1, and comes down. So let's check that. At 1 hertz, that's 2 pi radians per second. The gain ought to be right around 0.3. So let's try that. Here's my filter. I'm going to do it in 2 stages. There's the first stage, second stage. I could do it in 1 stage if I wanted. Let's see. Let's do a simulation. I'm going to plot x versus y. Input is 1 Hertz. Run. So the input is 1, and here's the output. It's about 0.278, about 0.3. Let's try another point. At 2 Hertz, that's too easy. 3 Hertz, about 18 radians per second. Gain ought to be a little bit less than 1. Let's try it. So the input is 2 Hertz, 3 Hertz, 18 radians per second. Simulate, run. Here's the output. The orange line. Peak is 0.728. So at 18 radians per second, the gain is 0.728. And if we go over to 4 Hertz, that's right about here, gain ought to be right around 0.4. So go over to 4 Hertz. Simulate, run. There's the output, 0.334. So that's what the graph tells you. As the frequency changes, it'll tell you what the gain is. That's filter analysis. Now, filter analysis is pretty straightforward. The harder part is filter design. With filter design, I want to add zeros, add poles, to come up with a certain gain versus frequency. Now, when you take signals and systems and circuits too, you'll come up with ways to do that. In this class, using Matlab, I can have Matlab design a filter for you. And here we're going to use a function called fminsearch. What fminsearch does is it will guess parameters to minimize the function. So for example, let's first come up with a function where I pass my guesses, a, b, c, d, e, f, g, and return the sum squared error between my guess and the actual filter. So here's what the function does. I'm going to pass z, that's my matrix of guesses, a through g. Here's what the desired response should be. The gain should be this function right here. I'll treat that as 3 straight lines between 0 and 2, 2 to 4, 4 to 6. So here's between 0 and 2, there's the curve. Between 2 to 4, the gain is 1. Between 4 and 6, there's the gain. Add them all up, I get the gain versus frequency. What actually it is, based upon a through g, is this one. Take the magnitude, take the difference between the two magnitudes, return the sum squared difference, and that's my cost. So if I try it, try 1, 2, 3, 4, 5, 6, 7, I get a cost. So let's try that. Here's my cost function. If I try running it, I'll get an error message. You can't run functions, but you can call them. So there's my error. Let's try cost f of 1, 2, 3, 4, 5, 6. Okay. 7. So what I wound up with is the blue line is what the gain versus frequency should be. The red line is what does the number 1, 2, 3, 4, 5, 6, 7 mean? The number 368 is how good my filter is. The sum squared error is 368. Can I make it smaller? So there's 358. Let's try that. A little better. A little better. So it's guess again, or let Matlab guess for you. So here I'm going to call the function fminsearch. What fminsearch does is it will say, let's minimize this function, cost f. Here's my initial guess. That's the resulting numbers and resulting error. Basically take those 7 numbers, can I do better? So in the function fminsearch, I'm plotting the result, which is kind of fun to see. It really slows it down, but it is fun to see. You can see Matlab guessing. And what's happening is I have 3 sets of complex poles. Here's the first pole, the first resonance, second pole, third pole. It's adjusting those poles around until I get that gain versus frequency. Now in Matlab, it'll kick out either after max iterations or when it finds the answer. Here, it's giving me a warning saying I kicked out due to max iterations. Here's the sum squared error, 37. Can I do better? Well, one way is just pick up where you left off. So Z was the current guesses of A through G. Let's use those same guesses. Can I reduce the cost less than 37? And you can see from the graph it's actually doing pretty well. And eventually it winds up with a cost of 0.795. So problem 5 is, here's a guess. If I want this filter, what's the cost? Just plug it in. If I have 72, that's A, B, C, D, E, F, G. Plug that in. There's the cost, 566, compared to the blue line. Not very good. Let fmin search optimize the numbers, and you get a cost of 0.769. There's my A, B, C, D, E, F, G, meaning here's my filter. Now, thing to note is fmin search is really useful. If you know nothing about filter design, you can design some pretty good filters with Matlab and fmin search. Once you take signals and systems, you can design these by hand as well, and there is a pattern. The poles and zeros aren't arbitrary. You can design them by hand, but with Matlab will also do it. So when you get to signals and systems, this is one way to design your filters. Then the challenge is, can I do better by hand? But that's one of the uses of Matlab. I can analyze filters. I can design filters. And that's homework set number 14 for ECE 111.